Hello and welcome back to this course on data science, fundamentals of data science. And we have discussed about the Markov chain process. And now we are into the new topics of queuing theory. So here is the contents for today. We are going to discuss about what a queuing theory is and how queuing theories can be applied for data science. And we are going to only focus on single server model. Here it is. We are going to define what is a queuing model and how a queuing model is used in real world applications. And queuing forms or it follows a FIFO pattern. It is first in, first out pattern. We'll see and we'll observe how it is done. And we are going to look at a single server model. It's kind of a Markov process, but with a single server, but infinite number of customers. It's assumed that it has infinite number of customers with a FIFO model. There are some conditions, some patterns, some properties, some characteristics of this queuing model. These are some of the things that we will discuss in this lecture. Let's directly go on to this introduction part of queuing theory. Well, queuing theory is a very popular model. It has been used in many places, but generally speaking, in real world, we always come across many places where we have the queuing theory. So there are a lot of things that we are going to discuss, starting from what a queuing theory is. For example, customers arriving in a random manner in a service facility, and then they stand in the queue. Upon their arrival, they are asked to wait in the queue until they been served. So once served, they are generally assumed to be leaving the system. So with these assumptions, we can actually understand how this whole process of queuing theory works. So average number of customers in a system or in a queue can also be calculated. Average time a customer spends in a system can also be analyzed. So these are some of the advantages, because once we know these informations, accordingly you can plan ahead of what is going to be in the future. When a customer arrives, what you should do, you will be aware of this. Well, based on that, let's see what are the other places we see queue in the real world. For example, you go to a bank, you're waiting in the queue sometimes. You go to the airline, you're waiting in the queue. Yes, queues are found almost everywhere. Even you can consider the queues like when you have your computers, you have different processes running at the same time. All these processes are kind of queued to the processor, and it has been accordingly scheduled with some time slice, and again various scheduling mechanism is used to execute those process. Yes, depending upon the service status, depending upon the number of servers also, the whole process change. We know that if you are waiting in a queue, and if there is more than one server, you know that the queue can get its service done quite quickly, and that's very different from single server. Yes, if a system is free at the time of arrival of a customer, the customers can directly enter into the counter for getting the service, and he can leave the system. Otherwise, he has to wait in the queue. And can you predict how much time he can wait? Well, as far as statistics is concerned, we have a well-defined queuing model which can in fact predict that. Well, we can also see the process over a period of time. The system may expire or experience the customer's waiting or service idle time. So customers' waiting time can be predicted, and the objective is that a system in which a manner that the average waiting time of a customer is minimized and the percentage utilization of the servers is maintained. So we don't want the servers to be idle. We don't want the customers to be idly waiting. We want to make sure that the server is well utilized and the waiting time of the customers is minimized. That is the main objective of the entire queuing process. So there are more examples. We use the queuing model like in place of toll gate, vehicles are in the queue, toll collector is the server, library students on the queue, counter clerk is the server, traffic signal, vehicles are in the queue, signal points are the servers, for example, airport runways, planes are in the queue, runways are the servers. So likewise, lot of real world examples you can think about when it comes to the queuing process. So as we have mentioned earlier, the single server queuing model is represented here. So there is one server and there are different customers. In this case, we can consider it as passengers. And these customers are waiting to be served. It's a very simple single server model in which you can find a queue as well as the server. So there are some customers always waiting in the queue who are to be served. So here's an example of multi-server. You can see there are multiple queues and multiple servers as well. So of course we have customers in almost all the queues. So this is a multi-server model, and there are different types of multi-server models are also available. At times you have only one queue and multiple server, but here in this case you have several queues and multiple server. So there are different modes depending upon the real world applications. Things might change in a different way. Generally speaking, this is how the multi-server model looks like. So queue is a first in first out system in which once you enqueue an item, it will be in the first. For example, in this case we have one is enqueued and one is there, it's been enqueued, and you can see all the 2, 3, 4, 5, 6, all things have been enqueued after one. So when the system gets its process, the first thing that is to be processed is the first thing that has entered inside. In this case, number 1 has entered first, so that will be dequeued first. 1 is dequeued, then 2 is dequeued, 3, 4, and so on. So that is why it's a first in, first out. So in computing and in theory system, this is a method for organizing and manipulating the data structure. Yes, it's a very simple system in which we can see whoever comes in first gets served first. Well, that's another scheduling mechanism. People also modified such scheduling mechanism based on some priority based scheduling. Anyway, we are not going down in that direction. We'll fix our focus on this queuing examples with first in, first out principle. So here's some of the characteristics of queuing, which are very important for us to understand the whole process. So customers entering the system should form a queue. That is one of the first principle. And if the server is free, then they will get the service. If the server is not free, they wait in the queue and then they get the service. Basically, in the real time situation where there are various systems, you can consider the number of queues may be more than one, the number of server may be more than one. So that's where you have parallel counters at times and parallel quick queues at times. Some of the characteristics of queues are arrival pattern of a customer, service pattern of a customer, queue discipline, system capacity, number of service channel, number of service stages. So these are some of the other characteristics of queuing process. Mostly we are going to fix our attention to these patterns, as well as we are going to look at the traffic density. How much is the customer flow, how many people are coming in, how many processes are coming in to be served. Arrival pattern of customers. In usual queuing process, the arrival is a stochastic, and it is necessary to know the probability distribution describing the times between successive customer arrival, or in other words inter-arrival time. It is also necessary to know whether customer can arrive simultaneously as a batch of customers coming in together, and of the probability distribution describing the size of the customers. So here we have some assumptions. The assumptions regarding the distribution of arrival has a greater effect upon the mathematical model of this queuing system. So a typical model used is that the arrival rate is randomly distributed according to Poisson's distribution. So that's one of the assumptions that we have. It has been distributed according to the Poisson's distribution. So the mean value of arrival rate, we are going to call it as lambda. That is the mean arrival rate of the customers into the system. Then service departure patterns, like it represents the pattern in which the number of customers leave the system after served. And departures may also be represented by service or inter-departure time, which is the time period between two successive services. The number of customers served per unit of time is called service rate. The customer comes into the system and they get served. So the customers served per unit of time is called service rate. So this rate assume the service channel to be always busy. No idle time is allowed in this case. And here again we have an assumption. Assumption regarding the distribution of service is also very important to form the actual queuing model. A general assumption that we have here is that the service time is randomly distributed and according to the exponential distribution. We know that the arrival rate is according to Poisson's distribution. The service rate is according to the exponential distribution. And the mean value of service rate, we denote it by mu, the rate at which it is being served. Okay. Service channel. The queuing system may have single service channel, and the customers may vary from queues. So we can note that the system can also have a number of service channels where the customers may be arranged in parallel or in series, or with combination of both parallel and series. So service channel is also another important thing in modeling the queuing system. So here is an example like a single queue nodes. So this is the basic single queue node where we have the arrival rate as lambda, service rate as mu, and they are waiting in the queue. Yes, queue nodes with just one server is given here. Queue nodes with one server with arrival rate lambda and departure rate is given in this system. And here in this system we can see there is only one queue is here. System has been arrival rate is there, but there are three servers, 1, 2 and 3. So this process is little bit different from what we have here, but in our assumptions, in our problems that we are going to discuss from now on is going to focus on a single queuing model, wherein we have only one server like this, a queue with one server, and the arrival rate is lambda and the departure rate is mu. That is what we are going to focus initially, but there is a possibility to also have this type of service model, which we are not going to deal in our class. Service discipline. So there should be some discipline in the service. So this is the rule by which customers are selected from the queue for service. So the service discipline that we have here is first come, first serve. We also call it as first in, first out. So in real time situations, as you can see, people comes in, whoever comes in first, they get served first. And another service discipline is random and priority. The random pattern, the customers are chosen randomly from queue. Sometimes they are chosen randomly from the queue, or a priority is given to your customers. Like for example, while all the vehicles are waiting in the toll gate, maybe a VIP vehicle gets a priority. Just an example. But again, in this class, we are going to only consider the first come, first serve model. We are going to see some examples only based on that. We are not going to mix up with other patterns. Only this pattern of F5, FO has been followed. Maximum number of customers allowed in the system. The maximum number of customers allowed in the system can be either infinite or finite. So in some facility, only a limited number of customers are allowed. Maybe you can consider a bank. Maybe only limited number of customers or can be in one building. Like, so number of customers are generally speaking are finite, but as we have seen in this queuing system, at times we don't have any specific information about how many customers are there. So number of customers in the system, we can consider it, sometimes it can be infinite. For example, you have a telephone booth, and the number of customers arriving at the telephone booth may vary, and we cannot define a finite number for the number of customers who want to use a telephone service. So that's why the model in which we are going to discuss, we consider the number of customers to be infinite. Calling source or population. The arrival pattern of a customer depends upon the source which generates them. If there are only few potential customers, the calling sources or the population is called finite. For example, just imagine there is a cafeteria in a school, and cafeteria attracts only those people inside the school. Probably the students and faculties can go to the cafeteria. Well, you have a limit. You have already a limit, a finite number. If there are large number of potential customers, over 50 or 60, it is usually said to be infinite. Classification of queuing models. This is another important part on which we are classifying the queuing model. You can see A, B, C, D, E. So the first A represents the probability law of arrival or inter-arrival time. So inter-arrival time, first part is A, and then the B is probability law according to which the customers are being served, and C is the number of service stations, D is the maximum number allowed in the system, in service as well as waiting altogether, and E is queue discipline. Queue discipline, like just for example, F5, FO is one of the queue discipline, first in, first out. So this is the basic queuing model. Let's look at some of the notions here. So the P of P sub n, here is the probability that the size of the population at time t is referred as P sub n of t, and P sub naught is the probability of a system being idle or free when it is free, and this symbol rho is the traffic intensity. Traffic intensity is defined by rho, and L sub s is average or mean number of customers in the system. LQ is the average or mean number of customers in the queue. L sub S, L sub W here is the average or mean number of customers in the non-empty queue. W sub S is the average waiting time of customers in the system. W sub Q is the average waiting time of customers in the queue. So these are some of the notions. Let's define some formulas as well. So we can see here is the model 1, MM1, as we have seen. This 1 represents the number of servers, and this represents the number of customers. So number of customers in the queue as well as in the waiting, and this is the service discipline, the first in first out. Okay, P sub naught equals 1 minus lambda by mu, and this 1 minus lambda by mu denotes the probability of system being idle at the time t. You can see that the same thing we have seen here, probability of the size of population at time t, and the quantity lambda by mu is called the traffic intensity, which is represented by rho symbol. So here is P sub n equals lambda by mu whole power n times 1 minus lambda by mu. LS is the average number of customers. LS is the system. Here we mean the number of customers in the queue plus the person who is getting served. So we can imagine if this is the queue, if this is the server, say one person in the server being served and the remaining person in the queue. So it means the number of customers in the queue plus the person who is being served currently. That's what here it's been represented by LS. And to calculate the expected number of customers or average number of customers in the system, we can use this formula, rho by 1 minus rho or lambda by mu minus lambda. And the average number of customers in the system can also be denoted by the E of n. LQ, the average number of customers in the queue. Here we mean that the number of customers in the queue excluding the person who is getting served. So here again, suppose one person is getting served, others are here. So LQ represents only this. You don't have to include that one. And to calculate the expected number of customers or average number of customers in the queue, we can use the formula rho squared by 1 minus rho or lambda squared by mu minus lambda squared by mu times mu minus lambda. And the value LQ can also be calculated based on LS actually here. Once you know LS, LS minus lambda by mu is LQ. So here is the formula for LW, mu minus, its LW is mu by mu minus lambda, WS is 1 by mu minus lambda, W sub Q is lambda by mu times mu minus lambda. So likewise you can also see for probability that n is greater than k, we have rho times k for the Q, rho times k plus 1 for the system. And there are a few more probabilities like probability of Ws greater than t, we have e power minus mu minus lambda times t, and rho is lambda by mu, that is traffic intensity. So with these examples, with these formulas, we can see this example here. A GS25 convenience store has one cashier at its counter and 9 customers arrive on an average 5 minutes, while the cashiers can serve 10 customers in 5 minutes. Assume Poisson's distribution for arrival rate and exponential distribution for service rate. Our question is, find the average number of customers in the system, average number of customers in the queue or average queue length, average number of or average time a customer waits before being served, average time a customer spends in the system. So first and foremost thing is that you have to identify what queuing model it is. Well, we are discussing about a single server model. There is only one cashier here. Since there is only one cashier, we say that there is only one server, and then you can think about other data is given to us. There are 9 customers arrive on an average 5 minutes, and also the cashier can serve 10 customers in 5 minutes. So based on the given data, we are going to calculate these values. So first, as I mentioned, we are trying to identify the model. It's a single server model, and we can see based on the service capacity, we can assume that we are in this model, first come first serve model, that is FIFO, or it can also be said as FIFO model. Okay, we have to understand the things to find what is the service rate, what is the arrival rate, and then eventually you have to find the average number of customers in the system, average number of customers in the queue, that is LS, LQ, WQ, WS is all the things that you have to find. So starting from this process, you can think about the arrival rate. Based on the arrival rate, you can find what is the lambda here and what is the mu there, and accordingly you can find the values for each of them, and you can use the system formulas here. All the formulas are given to us. Based on these formulas, you can calculate the given part. Well, here is another example, and this example, you can see the arrival rate of telephone calls at a telephone booth is according to Poisson's distribution with an average time of 9 minutes between 2 consecutive arrivals. So that's the first key. The average time of 9 minutes between 2 consecutive arrivals. The length of telephone calls is assumed to be exponentially distributed with a mean 3 minutes. It's a service time is 3 minutes. Determine the probability that a person arriving at the booth will have to wait. What is the probability that he would wait? Find the average queue length. You have to find this. The telephone company will install a second booth when convinced that an arrival would have to wait at least 4 minutes. Find the increase in flow of arrival which will justify a second booth. So here, what is the probability that the arrival will have to wait? Will have to wait for more than 10 minutes before being served. So with these questions, we have to find what is the probability that arrival will have to wait for more than 10 minutes before the phone is available and the call is also complete. Find the fraction of the day the phone will be in use. So with the given data, we can come to know that this is a model with only one server, and arrival rate is given as 9 minutes between consecutive arrivals. So lambda is 1/9 per minute and 3 minutes per service. So mu is 1/3 minutes. You can see the mean service time is 3 minutes there. And we have to find the other values, including the person's arrival at the booth will have to wait, average queue length you have to find, and other values as we have seen here. We also have to find the arrival value, you have to wait for more than 10 minutes before being served, for which we can use this formula there. So based on that you can calculate initially the rho is the traffic intensity or the density, lambda by mu. We have lambda and mu given to us, you can calculate, and LW, which is mu minus, in fact LW is mu by mu minus lambda. So you can calculate LW here, the average queue length, that comes to be 1.5. The average queue length is 1.5. The average waiting time in the queue, that is WQ, we have to calculate. So we can use lambda 1 here, as we have to use lambda already. So lambda 1, we have to just keep it as such as you calculate this lambda 1, because mu you already know, and with this informations we can use the formulas given here. For example, we can go back and see the formulas here. For probability that WS is more than 10, you can use e power mu minus lambda times t. So I will keep this two problems open to you to solve it. Just use the formulas directly. Directly using the formula you should be able to compute all the values as such. And as we proceed, I will also follow through this example so that you can also make sure you got the right answer. So I will stop here for the time being, and I will let you to solve the problem by yourself by using the formulas given to you. And this is what we have seen. We have seen the basic queuing model, and we have seen various characteristics of the queue, the properties of queue. One of the properties is the first come first serve, first in first out pattern has been followed in the queuing system. And basically we focused only on a single server model. There is only one server with infinite number of customers. It's open to customers more than 50 or 60. We consider it as infinite number of customers. And we saw simple examples. We already have all the formulas in hand. We can directly use these formulas. We haven't derived these formulas. These formulas are already well defined and well verified by the statisticians. We can use these formulas to calculate what is needed for us. And I will back up with you guys to understand how this actual problem works. If you have any questions with solving the problem, we can discuss in detail about these questions as we proceed with this online lecture on this data science. And you can see how this queuing system, though it's a simple model, a statistical model, we can understand what is the average waiting time of a customer, what is the average length of the queue, what is the average service time. So these things are very essential factors in data science, because at times we have to understand when a data are there in a server, we need to understand how much time does it take to be served, or how much time it has to wait. There are some data which has higher priorities, like for example healthcare data may have higher priority, and there are some data are not of higher priority. So your queuing model changes accordingly. So it has a very significant impact in data science. So try to get full benefit of this queuing theory. This is the very basics of queuing theory that we have seen in this class, but it can be extended in a very large way, including you can include some of the learning methods as well. I will just let this open to you so you can think about and contemplate on how this can be used in various ways. So that's all we have for the queuing model. And in our next lecture we are going to the next topic of linear regressions. So we will consider some of the basics of regression with certain examples, and we'll also see how some predictions can be made using regression. It's interesting that in Markov process we talked about kind of predictions, and in queuing model we talked about how we can identify arrival time, inter-arrival time, service time, traffic density, and so on and so forth. And again, in regression also we are going to see about the prediction models. I'm going to discuss in detail about this information in the next lecture. I'm looking forward to see you there. Until then, goodbye.